chaired by Professor Tina Thomas.
That's good.
I give you the word.
Okay. Good morning, everyone. Is this on? Get ready myself now. Okay, so we'll keep continuing with the photometric surveys, and these two next sessions, two talks, I should say, are on the dark energy survey, and Manda is introducing the survey to us.
Great, thank you. So thank you to the organisers for inviting me to come here and tell you about the dark energy survey. So we've heard about the dark energy survey already in Tom's talk, and in this talk I'm just going to tell you about survey progress and also present some initial early science highlights from the data. So, instead of my slide, is there a way to? No. No, it's just cut. Okay. It's just cut my slide. I could keep going and you only see half a slide. Okay, thank you. Yeah, so this is just an outline of my talk. I'll start by introducing Des, then tell you about some early science highlights, some synergies with other surveys, and then future prospects. So the dark energy survey is being conducted using this Blanco 4-meter telescope at CTIO. CTIO is here in Chile. As many of you know, it's an excellent astronomical site, very good seeing, about 0.75 arcseconds median, very high percentage of clear and photometric nights. And in late 2003, NOAO announced an announcement of opportunity for a new facility instrument for the Blanco telescope. And so this is how DE-CAM, or the dark energy camera, came about. So this is the dark energy camera here, seen at the Blanco telescope. It's a brand new 3 square degree field of view camera, 570 megapixels, which is now on the refurbished Blanco 4-meter telescope. And the Dark Energy Survey collaboration had 525 nights on this camera to conduct the survey over the next 5 years. But I'd like to stress as well that in addition to doing the survey, this is also a premier facility instrument for the rest of the astronomy community. And indeed, there are lots of other projects also ongoing with this instrument. So the really nice thing about DES compared to previous dark energy experiments is that the aim is to use a multi-probe approach to trace the nature and evolution of dark energy. So in particular, we're looking at cluster counts, weak gravitational lensing, large-scale structure, and a supernova survey. And it's really the combination of these probes that allows us to get a good handle on dark energy measurements. And to be able to do this, we're doing essentially two surveys. So the main survey is a 5,000 square degree survey going down to 24th magnitude and 5 filters, G, R, I, Z, and Y. And then there's also a 30 square degree time domain supernova survey. So I'd like to stress from the start that this talk is really on behalf of very large and very active collaboration. So currently there's over 300 scientists in the Dark Energy Survey collaboration in about 25 different institutes across 6 countries. So the USA, UK, Spain, Brazil, Germany, and Switzerland. This is how we're organized, at least in the science part of the survey. So the project office is headed by Josh Freeman, who's the director for the Dark Energy Survey. And then the Dark Energy Survey Science Committee is led by Ofra Lahav and Gary Bernstein. And then we're split into these 12 science working groups. So working groups to deal with the main cosmology probes, large-scale structure, weak lensing, clusters, and supernovae. These are the names of the co-chairs of the working groups. And then there's also a whole range of legacy science that's going to come about from the survey. So galaxy evolution, which Diego will talk to you about in the next talk, quasar, strong lens, and Milky Way. And then we also have working groups for simulations, photometric redshift theory, and spectroscopy. So as the name implies, one of the main aims of this survey is to get a really large improvement in the dark energy figure of merit measurement. So these are the current constraints from Sullivan et al. 2011 on the W0 WA parameters. And then this is what we can expect from the dark energy survey data. And it's really the combination of all these different probes that we're using together with the CMB prior from Planck that allows to get this factor of 3 to 5 improvement in the dark energy survey measurement. So that's the main goal, and the survey is already well underway. So we had first light in September 2012, and this is one of the first light images. This is the Fornax cluster seen through the DE-CAM field of view, and you can see here this is a really beautiful image of NGC 1365. And really one of the really nice things was that within the first few nights of the survey starting, we got down to 0.8 arc-second seeing. So again, this is showing you some of the first images to come out of the survey. Tom showed some of these already. So these are galaxy clusters seen in the dark energy survey data. You can see in some cases you see these strong lensing arcs, globular clusters, spiral galaxies. So lots and lots of data coming in already. So the current status of the survey, as I said, we had first light of the camera in September 2012, and this was followed by a month of commissioning between September and October 2012. Then between November 2012 and February 2013, we had a period of science verification observations where we covered around 300 square degrees to the full 5-year depth of the survey. And a lot of the science results that I will be showing you in this talk are from this initial science verification data. The year 1 observations are now complete. So year 1 ran between fall of 2013 and spring of this year. Our aim was to image 2,000 square degrees of the final 5,000 square degree footprint, go down to 40% of the full depth. So DES is a multi-pass survey, so we will build up depth of the next 5 years. We achieved 82% of the planned exposures. And year 2 has already started as of fall of this year. And our aim is to get the remaining part of the sky, so the remaining 3,000 square degrees, again to 40% of the final depth. So this is what our footprint looks like on the sky. So this tank-like shape is our final 5-year footprint. The red regions here are the science verification observations, so these now go down to the full 5-year depth. The blue regions here are what we've covered as part of year 1, so there's really nice overlap with the SDSS Stripe 82 survey here. And also this region here is covered by the South Pole Telescope Sunyaev-Soldovich survey, which I'll talk to you about in a bit. And then these yellow fields, these circles over here are deep supernova fields, and they overlap lots of ancillary multi-wavelength data sets, including the video survey, which Matt will talk about, Spitzer surveys, Herschel data, so lots and lots of legacy science potential in these deep fields here. Right, so this is what the survey strategy is. So as I said, we have this wide 5,000 square degree survey. These are the planned exposures. So we have 10 passes, 90-second exposures in the GR, I and Z bands, shorter exposures in the Y band. We have these seeing constraints in the RI, Z bands to enable us to do the weak lensing measurements. And then we also have this supernova survey. So supernova survey is split into a shallow survey over 24 square degrees and then a deeper survey over 6 square degrees. And the survey strategy is to do the supernova survey when the seeing gets worse than 1.1 arc-second. We can't do the weak lensing part of the survey. Or 7 days since the last observed measurement to get the right cadence for supernova observations. Right, so now I'll just talk about some early science results that have come out of this data. So this was one of the first papers to appear from the science verification data. This is a paper led by Peter Melchior in Ohio, showing the potential of the dark energy survey to do weak lensing mass map measurements. So these are a couple of well-known galaxy clusters. These are the GRI color composite images. And then what you see in the middle panel here are the weak lensing mass maps. And then overlaid as black points are red sequence galaxies that are found using this red mapper cluster finding algorithm. And the density of points of the black points just tells you the density of red galaxies. So really nicely, you see here that the red galaxy distribution, as you might expect, overlaps with the mass maps. The galaxies do really trace the mass in these clusters. But then the really unique thing about DECAM is because of the large field of view, we're able to do this kind of large-scale structure measurement over very, very large scale. So this is the central region that's shown in the middle panel. But now in this right panel, what's shown are again the red sequence galaxies, but going out to much larger areas. And you can see that the DES data allows us to trace these really nice filamentary structures around these clusters on scales of tens of megaparsecs. So another paper, so the references unfortunately disappeared, but another paper led by Carlos Sanchez that came out conducts a detailed study of the photometric redshift performance in the dark energy survey. So this is really critical for a lot of the cosmology that the survey is going to do, because it's really important to get a good handle on photometric redshifts to enable the dark energy measurements. So in this paper, we studied a bunch of different photometric redshift codes, including template fitting and empirical training set-based methods, and looked at a lot of statistics on the photometric redshift performance, including the bias, scatter, outlier fraction, etc. And we have quite stringent requirements on this because of the dark energy science that we want to do with the survey. So this plot here is just showing the bias on the photometric redshift versus the 1 sigma scatter. And then this line here shows you our science requirements. We need to be below this line to be able to do the science that we want to do. And we want a bias that's as close to 0 as possible. And each of these different points are for a bunch of different codes. And the really nice thing is even at the early stages of the survey, we're already getting down to very good photometric redshift performance. So we have a bunch of codes that are close to 0 in terms of bias and very low levels of photometric redshift scatter. So this is very encouraging for the future. One of the other unique things about DECAM compared to previous optical surveys is how sensitive it is in the red wavelength, so at infrared wavelengths. And this really opens up the high redshift universe to us in a way that hasn't been possible with surveys like SLOAN. So one of the things that Chris DeAndrea has done is looked for high redshift supernovae in this data. So this is showing one example. This is a supernova at redshift 0.9 that we've spectroscopically confirmed on the AAT. And you can see the light curves here peaking really nicely in these redder I and Z bands. Again, looking at the high redshift universe, DES also allows us to look for high redshift galaxy clusters. This is a new redshift 0.8 to 0.9 very rich galaxy cluster discovered by Eli Rykoff, Eduardo Rosso, and others using their red mapper cluster finding algorithm. You can see the cluster here, and then these red circles mark the red sequence galaxies associated with that cluster. Something else that we can do with the dark energy survey is look for high redshift quasars. And using the science verification data over 300 square degrees, we've already found the first redshift greater than 6 quasar. This is work led by Sophie Reed, who's a PhD student at the Institute of Astronomy, working with myself and Richard McMahon. You can see here, these are the cutouts, the optical GRI, Z, Y, and then the infrared JK cutouts of this quasar. Because of the Lyman alpha absorption, you see nothing in these optical bands, and then you see this very bright quasar popping up in the redder bands, and then this is the discovery spectrum, which confirms that the quasar is at redshift 6.1. Right, so as we've heard a number of times during this meeting, these surveys can't really work in isolation, so now I wanted to show some synergies with other surveys that are ongoing. One of the surveys that DES overlaps is the South Pole Telescope Senior-Fildovich survey. So a large proportion of the DES area will be covered by the South Pole Telescope. DES is expected to detect more than 100,000 clusters out to redshifts of 1, and we expect about 1,000 of them to have FSET measurements from the SPT. So this will be a really nice data set for all sorts of cluster science. Some early work that's led by Tommaso Gianantonio, what he's been doing is looking at the cross-correlation between the CMB lensing map coming out from the South Pole Telescope and the galaxy distribution that we have from the Dark Energy Survey science verification data. And when you combine these two, these are the correlation functions. This is the galaxy-galaxy correlation function. This is the galaxy SVT correlation function. So you see a really nice greater than 5 sigma detection of this cross-correlation between the galaxy distribution and the SVT data. And this is fit, the model fit is shown by the black line, and this is well fit by fiducial Planck lambda CDM cosmology. Something else that you'll be hearing about more today is the VISTA Hemisphere survey, which is one of the 6 ESO public surveys being conducted on the VISTA telescope. The VISTA Hemisphere survey also overlaps a lot of the dark energy survey area, and VHS is actually 3 surveys in one, and over the dark energy survey footprint, we actually go deeper than over the rest of the sky. So this plot is showing you the overlap of the VHS data we have so far, shown by the green areas, with the dark energy survey science verification data, which is shown as the blue points. And because we started earlier, we've imaged a significant proportion of the dark energy survey area already. So more than 3,000 square degrees of the final 5,000 square degree DES footprint. And a lot of that overlaps with the science verification data, which means that we've been able to combine these 2 data sets and extend the wavelength coverage of DES. So something that we've been doing is looking at the potential for using the dark energy survey optical detections to extract low signal to noise fluxes from the VHS data. So VHS is by design much shallower than DES, but the idea is because you know where the galaxies are from the optical imaging data, you can go to those positions in the near-infrared images and measure fluxes, albeit at lower signal to noise. And this is why this is helpful. So what's shown here are number counts in the J and K VISTA pass bands. The blue curves are the number counts from the VHS 5 sigma catalogs. You see they turn over here around 20th magnitude. The green lines are the number counts from the much deeper video survey, which Matt will be talking about. And then the red line is what we get when we use the DES detections to extract fluxes from the VHS data. So you see it allows us to push to fainter near-infrared magnitudes, about 1.5 magnitudes fainter than if we would just do a simple positional match based on the catalogs. And it allows us to increase the number of galaxies with infrared flux information by a factor of about 4 relative to a simple catalog match. So we've been looking at what we can do with this joint data set, and one of the things that we've done is to try and select high redshift luminous red galaxies using this matched catalog. So we've done this really simple selection for now in the R-Z, Z-K color plane. This is where the galaxies generally lie. These are the tracks of a red galaxy, these are the tracks of a blue galaxy. And these green stars, I don't know why it hasn't come up, but these green squares are the colors of known M stars. And so we select galaxies in this box with the aim of finding this high redshift red galaxy population. And then we have a program on the AAT, which I'll talk about in a second, that allows us to get spectroscopy for these targets.
What color do you have on the wire?
Sorry, this is Z-K.
Okay.
Thank you. Yeah, sorry, a lot of this is chopped up. So R-Z versus Z-K. And so this is the redshift distribution that we get. So we get this redshift distribution that peaks at a redshift of 0.72. So we are able to select high redshift galaxies using high redshift red galaxies using this selection. And really the aim of this was to assess how useful these catalogs will be for doing target selection for future redshift surveys like Foremost and DESI. And looking at the spectra of these objects, we confirm that these are all early type galaxies with prominent Balmer breaks. And we get very little contamination in this selection from things like M stars, which have been a problem with optical only color selections. So I've mentioned OSDES already. So OSDES is an approved long-term AAT program. It's a 5-year program. The PI is Chris Littman, and it's a collaboration between the Dark Energy Survey and Australian scientists. And really this picture highlights to you the beautiful synergy between the 2 instruments, between DECAM and AA omega. So the white hexagon here is the DECAM field of view, and then overlaid on it is the AA omega field of view, which you see overlaps it really nicely, and these red circles here mark the positions of fibers on the AAT spectrograph. So the primary goal of OSDES is supernova follow-up, so to get spectroscopic confirmation of supernova host galaxies. But of course, you can see there's lots and lots of fibers overlapping each DECAM pointing. So there's a lot of spare fibers available for interesting ancillary science. And we're doing a number of things with this survey. So one of the things that we're doing that I think is very exciting is doing AGN reverberation mapping, because we will get multi-epoch spectroscopy in these fields from the AAT. And what that will allow us to do is to calibrate black hole masses at high redshift for the first time by looking at the variability in the emission lines in quasar spectra. We're also following up dark energy survey clusters, strong lenses, as I showed you in the previous slide, testing target selection for future wide field spectroscopic surveys. We've already had more than a year of OSDES data, and there's a paper in prep that will hopefully be coming out soon, presenting the initial data from this survey. So that's pretty much all I have to say. So just to conclude, DECAM is a high-quality science instrument that's already delivering excellent science data. We've already got some really nice data as part of the Dark Energy Survey collaboration. There's lots of science papers that are currently being written from the science verification observations, plus analysis of year one observations, which are now complete, is ongoing. Some of the highlights have included mass reconstruction, studies of clusters, photometric redshifts, discovery of high redshift quasars, discovery of high redshift supernovae, some studies of the Large Magellanic Cloud, which has been submitted, which I didn't have time to present in this talk. Lots of synergy with all the other surveys that are ongoing in the southern sky, including the South Pole Telescope, the VISTA surveys, and then we have this 5-year program on the AAT, OSDES, which will get spectroscopic follow-up for a lot of the DES galaxies. So yeah, many more papers to come over the next year, so watch this space. Thanks.
Right. Questions? Let me start by first. You showed the photometric redshift accuracy plot. There were various methods being tested, and some performed better than others. Do you just want to comment a bit which were the ones that were better, and maybe also something about the comparison between methods?
Yep. So is it possible to go back to that? So yeah, in this study, there's both template fitting codes and empirical training set-based methods. Yeah, that was studied. And this group of codes here that have very small bias and very low scatter are generally the training set-based estimates. So they're generally the things, so things like machine learning-based codes, and some Zebra is actually, no, Zebra isn't that. But some of them are hybrid methods as well, which use templates to train the algorithm. So I think those do pretty well as well. But most of these are training set-based codes.
Up to which redshift?
This is going to redshift about 1.
Yeah.
Yeah.
So about.
Yeah. No, you can't use training set-based. No. Yeah, but the majority, so this was, I mean, the aim of this paper, I should stress, is for the cosmology. So these science requirements are set by the cosmology goals, which is going to use, So
you don't need those science requirements at higher redshift.
Yeah, so they're not going to be using the high redshift stuff for weak lensing. So yeah, exactly.
Okay, that's a question over there.
So just to chase this down a little further, in this comparison, the training sets were in the same area of sky as the imaging, the imaging was used to do this test, is that right?
Yes, that's right.
So, of course, in the whole survey, that won't necessarily be the case.
Yes.
The training sets will be in certain places of the sky.
Yeah.
And the critical aspect of bias will be carrying the integrity of the calibration of the photometry across the entire survey.
Absolutely.
Can you comment on where we're at with that?
Sure. So there's a number of things that we did in this paper. So the first thing was to actually train on one patch of the sky and test on another patch of the sky, and to check for systematic. So Carlos did a number of tests on that, and we found that the results were robust to those. And then the other thing that we did was, because the magnitude distribution of the training sets are currently not well matched to the DES data, because the spectroscopic training sets that we have are generally a lot brighter. So when evaluating all these statistics, the galaxies are actually weighted, so that they're weighted by their magnitude distribution. So we don't we take into account the fact that the spectroscopic training sets are much brighter than the photometric sample that we're evaluating the redshifts on.
Yes, we have a question here and then Tom.
Well, a comment on the question, to answer the question, we did extensive testing within empirical method already little affected by the distribution of thin plate objects with respect to the distribution of the photometric sample. And my question is the following: how did you evaluate the PDF for the empirical methods?
How do you?
The probability density function for the errors, basically for the empirical.
Yeah, so I think the number, so some of these, I can't remember off the top of my head which of these do and which of these don't, but I think some of the empirical methods do give you a full probability distribution.
Empirical methods?
Yeah, some of them do. So for example, the TPZ, so the things that have P of Z next to them.
But that one gives you the internal errors. The one used to random initialization of the weights doesn't give you the correlation with the photometric error. That is a long-lasting.
Right.
I wanted to know if you solved it, because I think it's
so in the
main problem to solve with the empirical methods.
In the neural network method, for example, in ANNZ, the photometric errors are propagated to give the final error on the photometric version. But that doesn't give a PDF. Yeah. So I'm not sure about all of these methods, what's done with the photometric errors, but I believe the details are in Carlos's paper, because I mean I'm not familiar with all of these codes. There's a lot of them on the market, so yeah.
Okay, Tom.
I'm quite confident that it's about getting the seeing down to the 0.907 spec for recleansing, and then further down for the level of kits have got 0.7.
So I don't do weak lensing, so I don't feel comfortable commenting on that. I mean, I think from what I hear from the collaboration, the weak lensing people are happy with the seeing that they're getting from the telescope at the moment. So certainly they've been looking at the year 1 data and they're happy with the seeing that they've been getting from the data. But you have to ask them for more details.
Okay, excellent. Let's thank Mandar again. So next is Diego Capozino. He will tell us about galaxy evolution projects with the Dark Energy Survey.
Okay, hello everybody, and first of all, thanks for allowing me to speak at this conference, and happy birthday to Massimo. So today I'll give you an update of what we've been working on with regards to galaxy evolution, in particular on luminosity and mass function. And I thought to start to talk with a very general statement, so and with a very standard picture we know very well. So the whole dark matter paradigm that we use to predict structure formation implies hierarchical structure formation, and is a paradigm that works pretty well when we talk about dark matter, obviously, and when we use galaxies to predict the clustering and the structure formation. So let's say the galaxies work pretty well in tracing dark matter on scales larger than 10 megaparsecs. Now, this we can also see in recent results. I just picked up 2 recent examples. One thing just from data, from observation. You can see here the very good agreement between the observation of the BAO bump in the cross-correlation function measured via the Boss collaboration with the models. And another aspect here is when we compare with simulations as well. This is a very standard picture from Springer 2006, where we see several SDSS, in particular CFA and and 2DF which are spectroscopic survey, which are very well reproduced when using simulations, which are the corresponding red plots. Now, within the concordance, and this works well within the concordance cosmology, and within this concordance cosmology, we can think of halos being described by universal scaling relation, and within this halo, these virialized halos, we can think of galaxies. So galaxies reside in these halos, and then how galaxy populates these dark matter halos. We can think theoretically about doing it by simulating models or the halo model formalism, for example. But when we think about it, it's very much understanding the mutual relation between dark matter and baryonic matter, which is very much close to try to answer the following question: how do galaxies form? I challenge you here to answer this question. I don't think it's very easy to answer. Also because it involves many processes which aren't necessarily related with gravity only. But the other question is then, despite all the processes that are involved in the galaxy formation, is still gravity the main driver? If we think about the current galaxy formation scenario, then we might reply with a yes. So stars form quickly in subgalactic halos, and then they emerge over cosmic time. But then we need to check whether this statement actually agrees with what we observe. And I just put some questions. So within this hierarchy of pictures, so small galaxies form first, then bigger ones. Does this scenario reproduce the color-magnitude relation of early type galaxies? Does it reproduce luminosity and stellar mass function? Or can it reproduce galaxy chemical enrichment? And so we've seen there was Gabriella also talking yesterday. She focused also on this chemical enrichment problem, for example. So there are things that have to be solved. And one of the main concepts we have to remember is that galaxy, when we think about galaxy formation, a galaxy can experience two moments: the formation time of its stellar content and the assembly time of this stellar content. These two moments may coincide or may not. And if we focus, for example, on a paper that Gabriella has done in 2006 about early type galaxies, when basically the assembly time of the stellar content of galaxies was studied in these galaxies, and by here it just plotted the fraction of stellar mass assembled onto the main halo as a function of redshift for two subsamples of early type galaxies. So the shaded histogram refers to more massive ones, more massive than 10 to the 11 solar masses, while the remaining histogram refers to masses higher than 10 to the 9 solar masses. And you can see that basically what we see that the most massive ones assemble later, and this is basically what is the prediction of hierarchical formation in the end, and which is also the premise of many simulations. However, when we focus on the number density of galaxies in observation, when we focus, for example, on the study of stellar mass function, we can see, for example, the results of Otseki et al., where they studied the stellar mass function in the cosmos survey. And if we focus on the results in the beams of stellar mass for different kinds of types of galaxies, we can see that the evolution from redshift 1 to redshift 0, the number density, depends on the stellar mass. And it's pretty much null. There is no evolution for the most massive ones. And it becomes to appear more evident as when we go towards lower masses. And another way to look at it, just when we check the plot, where on the y-axis here is the redshift at which the number density of galaxies were half of what we observe at redshift 0 as a function of stellar mass. Here is basically what is found in the observations. And this is what is obtained when we look at 3 different models, simulations. So they go opposite way. So this one will tell us that actually the most massive galaxies are the ones that form first. So it's the what is called downsizing or upsizing scenario, entire area. There are many names. Sorry about that. Okay. So the Cosmos results, however, were basically obtained on an area which was lower than about 2 square degrees. So it could be still affected by large scale structure. And from, maybe you don't have a large volume enough to see the evolution of, especially of the most massive galaxy, but you need volume. So one should actually focus on the BOSS results, because, for example, in this case, we have a large area, which is about 1,000 square degrees, and we're talking about spectroscopic survey, which was targeting massive galaxies between redshift 0.4 and 0.7, and where Claudia Maraston led this paper studying the stellar mass function for this survey. So here is the number densities plotted versus stellar mass. The red dots are the results of the BOSS survey. The blue squares are basically simulation by Bruno Enriquez in Munich, where basically the simulation were matched to reproduce the characteristics of the BOSS survey. The other data points are other observations of the stellar mass function found in the literature. Stopping now and just focus on these plots, we can see that there is very low or no evolution of the most massive part of the stellar mass function. And the reason you can see this drop is just because, as I said, BOSS was targeting massive galaxies, so there was no, so there is a sort of, there is incompleteness kicking in, and mass is lower than about 10 to the 11 solar masses. So when you compare, and then you can see that generally the models are slightly below the observed data points. When we then compare with redshift 0, we can see actually that the models actually start being on the top of the observed data points. But the other thing to notice is that the number densities of the massive ends at redshift 0 are actually lower than what we observe at higher redshift, which is completely counterintuitive, and we don't expect that. And that raises the question whether we have volume problems in the local universe, especially for the most massive galaxies. So what we can do better? We can do better in terms of going deeper at higher redshift. So we basically increase our volume. We can observe more massive galaxies, for example, if we focus on the massive N, where basically we can increase our statistics because the most massive galaxies are the rarest ones, so we need a large volume. And that's where the ES comes into place, because it's fairly deep and has a very large area, 5,000 square degrees, and we can actually go up to redshift 1.5, where you observe about about 4 by 10 to the 8 galaxies. So I'm not going into details about the ES because Manda explained the survey. Just before going into talking about the galaxy luminosity and stellar mass function with this, basically we aim to do a lot of stuff within for the galaxy evolution in the ES. But for today, let's focus on these observables. So for our study, in this case, we use science verification data. And one thing we wanted to make sure that we had, we basically focused on areas in the sky where the limiting magnitude of our galaxy sample was constant. And so that's a problem because obviously this limiting magnitude varies in the sky. That's what we have in the ES. So we had to make sure to handle this issue, which was done by constructing a limiting magnitude map telling us what was the dependence of the depth of our survey as a function of the position in the sky. So this map was pixelized. So in each pixel, we actually had this information. So what we did is just selecting areas and pixels with a given minimum depth, which in this case was 23 in the I band, and then selecting galaxies all in these pixels and get rid of all galaxies which were fainter than this limit. By doing that, we identify a region which is homogeneous in depth by construction. We identified basically 150 square degrees and about 5 million galaxies. So what we need to do then is estimate the galaxy probabilities that we need to study the luminosity mass function. We did this mainly by SED fitting, using 32 star formation histories, 32 templates that we use basically to fit the galaxy SED. And the main star formation history models are 4, which are exponentially decay model, simple stellar population, a truncation model, which is just a step-like function. So the star formation rate is constant for a period of time, and then it drops abruptly to 0. And then a constant forming model. Then we also focused on estimating obviously decay correction and detectability related properties, which we needed to fold in to estimate the luminosity mass function. And then we're using photometric redshift. I remind you that DS is a photometric survey, it's not spectroscopic. And in this case, we're using photometric redshift estimated by a neural network, in particular by pointed out. Okay. And then we estimated the completeness as a function of surface brightness and apparent magnitude. So after that, you estimate the absolute magnitude limits and stellar mass limits for completeness as well, which you need also to use to exclude beams in stellar mass and luminosity function that can be fully exploited. And these are the results, preliminary results on the luminosity function first. Here is the number density as a function of absolute magnitude in the I band. The red line is a fit only at the lowest redshift beam, which is then overplotted as the redshift increases from 0 to 1. And we only see a short noise, and I point out Eddington pi is not included yet, which is the next step we want to do by folding in the errors on photometric redshift. And I point out that there is evidence here that a single Schechter function is not really working to fit data. We need, in this case, a double Schechter function. And I point out that we are only using 3% of the final footprint of the ES. Then, if we focus on the stellar mass function, the plotting scheme is the same as before. And I point out on these two redshift beams where we overplot, we compare with the BOSS results, which I point out is a spectroscopic survey. So the fact that we here, for example, are in agreement with the BOSS survey is fairly reassuring for us, because we're using photometric redshift and BOSS is spectroscopic survey. So even also here we see that we need a double Schechter, at least to fit data fairly good. And another thing that I point out, which is probably more obvious here, when we plot the cumulative number density function as a function of stellar mass, different redshift beams, the black are the lowest ones, is the problem that I was pointing out before, that at the lowest redshift beam, the number densities are lower than what we observe at higher redshift. And again, this could be a volume problem, and since this is found also with spectroscopic data, it might be something real. We're looking into this now. And I leave with my conclusion that by using size verification data, we estimated, we studied luminosity mass function in a redshift range between 0 and 1. And then we can't use a single Schechter function to reproduce our data. And basically, we find agreement with BOSS, which is a spectroscopic survey, so it's reassuring. And then obviously the next step is folding in the errors on photometric redshift to properly estimate also the addendum bias and so on. And I thank you.
Thank you very much, Diego. Questions, comments? Something I, yes, let's start here.
So, a couple of questions on possible issues, because the fact that the right end is suppressed, but the massive end is suppressed, which is, as you said, disturbing. A long-run problem that Sloan had was in measuring the full magnitude of large galaxies, special galaxies and clusters, for example, getting out far enough into the light distribution to actually capture the brightness of those objects. And depending on the details of the photometry code, might be both you and BOSS might be getting bitten by similar kinds of problems that will manifest as a function of redshift because of the changing sizes of things.
Yeah.
So has much thought gone into that sort of issue yet?
I think I see what you're saying, and obviously we need. I think we need to investigate it properly. I think that at the moment that's a possibility that we might have problems as well, especially in crowded regions where it's much more difficult rightly identifying the total flux.
And that's where the biggest.
Yeah, so that's an issue that we are checking into.
And the fact that you agree with BOSS just maybe the BOSS has the same problem with photography.
Yeah, of course.
And then.
So it's not the case for both.
Now, you want to
Mariangela Bernardi has recalculated the mass function in redshift 0 for the Sloan, and there the point of the light profile is much more severe at lower redshift, of course. So I reckon the BOSS is not the problem for the redshift 0.5, and Mariangela has rectified up the lead in white redshift 0 mass function. So actually, with the revised redshift 0 mass function, the mass function does not evolve, and we get rid of this singular at the redshift 0. So the discrepancy. So I reckon the redshift are okay in this case, and the redshift 0 is affected.
Well, that's
probably sad.
Yeah. There's also another issue that the redshift 0, you have very low number statistics as well. So that's also an issue.
Okay, a quick question I wanted to ask is, so you showed the results for the deeper science verification survey. Have you looked at how far redshift one could go with the first year that Amanda presented, where obviously you're shallower but have a much larger area?
I mean, I haven't looked into that yet, but definitely, I don't think we can go up to redshift 1 because we just probably half as deep as 40%. So I guess it's gonna be maybe around 0.5, 0.6.
Okay, great. Let's thank Diego again.